So last time when we met, we talked about the behavior of a particular problem. Um, it was fairly simple, and we were able to do it by hand. You recollect that? Did I upload the notes? I thought I did. It was difficult, but I managed to find an FTP server that worked and uploaded it. But what we talked about, and we're actually going to complete that story to the extent possible today. But move this out of the way so I can use it from here. So we've had a lot of fun looking at the section moment curvature response. We understand that the section moment curvature response depends upon the axial force. We understand that you can obtain it by developing a moment curvature program that accounts for plane sections, remains plane, assumes the centroidal strain, increments the curvature, and all of that. And we realize that the moment curvature can be idealized or can be understood. There are three possibilities. Curve number one, which is the one that has the mean, is the one that you get from directly integrating the moment curvature response, if you account for all the residual stresses and the shape of the cross-section. You can, of course, idealize it to be elastic, perfectly plastic. That becomes option number two. And our third option is where we just model it to be rigid, perfectly plastic. And I told you that all three of these we can take into account and use to evaluate a given system. So what we did was we made the first idealization to be elastic, perfectly plastic. That's curve number two. And we looked at solving this problem, which is a fixed beam. It's fixed at both ends. And it is subjected to a concentrated force acting at a distance of 3/4 m. And the properties of that cross-section were given. We had the moment of inertia I, we had the plastic moment 1500. But when I go to build my finite element model, as you can imagine later, I'm going to need a little more. So it's a W14 by 26. So I looked it up. It's a W14 by 26 cross-section that we're looking at over there. And then we did what would be referred to as an event-to-event analysis. We went through doing sequentially elastic analysis by introducing plastic hinges. Since each hinge is elastic, perfectly plastic, I can do an event-to-event elastic analysis. So in the first analysis, we were able to calculate the elastic behavior, the corresponding deflections. Now, where would I get the bending moment diagram and deflections and rotations from? Do I have to solve this by hand? Well, I can find it in my AISC manual. As you know, there are tables there given for all different kinds of loading conditions and so on. So if I was ever hard-pressed to find the exact displaced shape for little v or little theta or the bending moment diagram, I'd have to just open my AISC manual, turn over to the tab that shows all the bending moment diagrams, equations, and I'd be able to find it. And I would be looking for the case where you've got a fixed beam, both ends fixed, and the load applied at a distance a, and it will give me the equation as a function of a. I'm sure you know what I'm talking about, but it's not like I'm expecting you to solve it. And besides that, I did tell you in the exam, I really don't want you to even try to calculate the v's and the thetas. I really don't care for them. I just wanted you to do the event-to-event analysis using the software. Because you're already doing a lot developing the entire moment curvature as a function of p for both a doubly symmetric cross-section and a singly symmetric cross-section, yeah? So here, of course, we did the elastic analysis. We found where the first plastic hinge occurs. We introduce that hinge, then do an incremental analysis, as you're seeing here, and we go through all of this. We keep incrementing the response until I get two plastic hinges. Then again, we introduce those hinges and continue with our incremental elastic analysis. At the end of the analysis, we end up with a bending moment diagram that has got MP at 3 different locations, and we've got the overall behavior. These are all part of your notes, so I'm not going to talk about it in detail. What I'm trying to do is remind you of where we were. That was the incremental response. That was the total response. We had now figured out that the system was in equilibrium. Some of our major conclusions were summarized here as points 1, 2, and 3. After completing this event-to-event analysis, the system was in equilibrium. It's going to be in equilibrium. We use static equilibrium at every incremental step. What was more important was that the moment was less than MP everywhere. It was either MP or less than MP. The moment nowhere exceeded MP. That's important because it can. And finally, there were enough hinges to form a mechanism, and the structure was at its plastic limit load. So that was what we got from the event-to-event analysis when we did it by hand. And we were able to draw out the total load displacement curve. That's the P versus V curve. And we just summarized some bullets. We said that all we did ever was elastic analysis. We didn't really do any inelastic analysis. We just did elastic analysis, introduced a plastic hinge, continued with an incremental. Since we know how to do elastic analysis, that's really, really doable. That's something that we can do. And we were doing some scaling of the results. Every time we did this analysis, it was just a unit load. The structure was changing, but the load was unit, and we were increasing it. It was really logical how we went about doing it. And after we were done with it, we had the complete load displacement path. And that's really where I stopped, where I said, there are two paths in front of us that we can take. One is the path where we continue the event-to-event analysis. Part, difficult path. And then there is another easy path where we do directly calculate the plastic limit load by mechanism analysis. And both of those paths we are going to explore. In the first path, we will not do it by hand, though. We will use a computer in order to do the analysis. Because if we did it by hand, all we'd ever be able to do was solve beam problems, or maybe a portal frame, nothing else. So what I'm showing you here in this, in my laptop right now is the model that I built in order to solve the same problem using Abacus. And you've already seen some of it, so I won't bore you with all the details. I won't rebuild it from scratch, but I'll show you really quickly how I built this model. So once again, you go back all the way to your original, as you open Abacus, you start defining a part. And the part that I defined was a 2D deformable body. Remember, if I ever want to see all the details, I can just ask it to show me the model tree. And when it shows me the model tree, it shows me the parts, the materials, the sections, the profiles, the assembly, everything. So I can always open and look at it in more detail if I wanted to. What was the feature that I drew? I can always double click and take a look at it. And it's telling me it's locked. Please don't ask me to unlock it, but I don't want to do that right now. But there's a model tree that can always show me where I am, what I built, and I can unlock it. And if I really want to make a specific change, I can make a change in that model tree. In any case, we built a what was just a beam problem, and the length was equal to 100 inches. So we went into the part module and defined a 2D deformable part, and that's what was just a simple straight line. The next we defined was the material properties. It was just elastic, perfectly plastic, steel. So the elastic modulus was 30,000, just as that was used in the hand calculation was used 30,000, not 29, that's why I put it in. And the plastic was 36 KSI was the beam that was being used. So that's why I've got it at 36 KSI. Okay? A992 steel is 50 KSI yield strength, so you'll be using 50. In this design example, I'm using 36 just because I'm doing the same example that we solved in class. Once we've defined the material, the next step is to actually define a cross-section. And here I have named it W14 by 26. There's no 14 by 26 for you to select. You need to actually put in all the parameters. So what you would do is you would select that section integration during analysis. You'd come up with a profile name. So in order to define your profile, all you'd have to do is click this, and it would start asking you, what kind of a profile do you want? Is it a box shape, a pipe shape? It gives you many different options that you can use to define your cross-section. Clearly, I'm using an I section, right? So I'll select the I shape. For the exam, you've got one is an I shape, the other is a T shape, and both of them are available as options that you can select. Does that make sense? So you'll be able to define the profile cross-section. And of course, you can also have an arbitrary cross-section. An arbitrary cross-section doesn't look like any of those shapes. It could be some random collection of elements. You can definitely do that. And you can also put in a generalized cross-section. In a generalized cross-section, you don't put in any dimensions. You directly give it the moment of inertia Ixx, Iyy, and you give it some of the parameters that it needs in order to be able to define it. So you actually don't give a shape. You directly give it the cross-sectional properties. So in this case, we selected an I shape. When you select an I shape, it gives you all of these options to define what the cross-section look like. And there's only one thing I need to explain to you, that's little l here. Do you see little l? Little l is this parameter right here, and that's the location of the centroid. So for the wide flange, it will be equal to half the depth. Should not be a problem. And the dimensions B2 and B1, as you can see, they can be different. T1 and T2, T3, all of those thicknesses of the individual element. So you'll just write in all of those numbers right here, end up defining the cross-section.
L is the area centroid, not the elastic centroid.
It's the elastic centroid.
So for the T-shape is the elastic centroid, so in a T-shape
it'll be summation of AI by I divided by yi. So it'll be summation of right? Y bar. And you can notice where it's being defined from. It's being defined from the bottom of the cross section. So you'll put in all those properties. If you ever get stuck while working on it, remember there's a big Abacus help manual that you can go in and read what each of these terms are, right? So don't get confused. If you do, you can always find help. So that's how I define the cross section. I'm not going to put in the properties right now because I've already put it in. You also get to select the material. In this case, I've selected the material that we defined, elastic plastic with 36 KSI. You can also define a new material. If you haven't yet defined it, you can go ahead and define it right here. So it's telling you, hey, is it a new material? Go ahead and define it. And the section Poisson ratio, I didn't give it one. We don't need it for this particular example. But there's a button there on the top that's saying something. It says during analysis or before analysis. So what this program will do is it's going to do the same thing that you're going to do when you develop your axial force moment curvature analysis. The program is internally going to discretize this cross-section into fibers. And what it means by during analysis is that it's going to keep integrating the stress states over the cross-section while doing the analysis. So it will do a fully material nonlinear analysis. So what it means is that when you're asking it to do it during analysis, internally the program will take your cross-section, it will divide it into several fibers, and use those fibers to come up with the moment curvature response as a function of axial force acting on the cross-section. So it will do what we will refer to later as a fiber analysis of the cross-section. But it'll do a little bit more than that. It'll do a fiber analysis through the depth, but it will also do that along the length of the member. So it will account for plasticity occurring here and the spread of plasticity as it occurs along the length. It won't be a closed form solution by any means of the word. It will be an approximation, just like any finite element approaches, but it's going to account for the spread of plasticity along the length. Which means that when you're doing this analysis, you're using option number 1. Remember we had 3 options. This was 1, this was 2, and this was 3. So when you do this analysis using a finite element software, you're more often than not introducing option number 1 directly, which means that it will calculate the overall behavior and plasticity along the length and all of that, which means that you can't do much better than that. The only way you can improve upon this kind of a nonlinear analysis is to use a lot more finite elements along the length. Won't be able to improve much more on the analysis results that you get. So it will be a fully nonlinear, material nonlinearity based analysis, and that's why it's asking you, do you want me to do the section integration? Now you understand what it's asking you. Do you want me to do section integration during the analysis, or do you want me to do it before analysis? What before analysis means that it will generate a moment curvature before the analysis and keep it. The problem with that is it is not going to be as accurate when the axial forces change or when the loading changes. So right now I have axial force equal to 0. So whether I do it during or after analysis, it won't make a difference. But when I have axial force introduced, I probably want to stick with during analysis. And that's why it's been introduced like that. So that's the big thing, is defining the cross-section. The next thing that you need to do is assign that cross-section. So you can assign that cross-section to that particular part that you've designed. So you would select it and assign that cross-section to it. Since there's only one cross-section, it's not going to be that difficult. So for example, if you click this, you'd select this as the cross-section, and then it will ask you, well, since you have only one cross-section, you can select it, or you can define a new cross-section by clicking the icon next. So that's how you would define the cross-section. But before you get out of here, you need to do one more thing, and that is you need to assign the beam orientation. So this is a new step as opposed to what you've done before. For those of you who've used SAP 2000 or any other beam analysis program know what I'm talking about. It's wanting to know the axis of the beam. What is the direction of the axis? So it wants you to assign the beam orientation. Do you know what I'm talking about? Every time you use SAP 2000 or any other beam column analysis program, it will ask you to define the beam column, and it will ask you for the node I and the node J so that it can figure out what the direction is, so that it can use that internally. In order to assign the beam orientation, all you need to do is click it. You need to select the beam, and then it'll ask you, enter the approximate n1 direction tangent vector. I entered it as shown here, and that's why I'm getting axis like that. And that's how I've defined it. And after you've done assigning the beam orientation, you will be done with this portion of the design, of the module. Sometimes while assigning the beam orientation, you may have to select a node here and a node here in order to define the tangent direction along the length. It depends on how so watch for the keywords down here. It'll ask you information on how to assign the beam orientation, and you'll be able to assign it accordingly. After that, you get to the assembly. This is pretty straightforward. You don't have to do anything. It just shows up. It's the only beam element that's there. Now, one thing that you need to do here is introduce the node associated with applying the force. So you can do that using the partition edge tool. You all used it last time when you did your exam number 1. In this case, I need to partition so that I can have that node when I'm going to apply the force. Remember, that was at 3/4 L. So I need to put in an actual physical cut in the part so that I can select that location as a node. The idea is it wants to do the analysis free of the mesh. It doesn't want to depend on the mesh. Of course, in other finite element programs, you define the mesh and then you come back and define the load. It doesn't want to do that. Instead, it wants the load and displacements to be defined in the part, which means that in the part, you need to position a reference node right there, which you can do by cutting it. So you select the cut tool and provide a partition at 3/4 L, which will put a node right there. Do you see that? It's broken up into 2 lengths now. One is 25%, the other is 3 to 75%. And you do that directly by just selecting the partition edge tool. It'll ask you to specify the parameter. It's telling you it's locked. I don't want to mess around with it right now. But it'll ask you how far do you want it, and you can give it 0.75 in it. Okay, the cut right there. Once that's done, you can go to the step module. Now, here, you're going to define your analysis steps. I'm just using a static general. You can use a little more fancy things, but I'm not going to introduce that right now. And I've still kept the nonlinear geometry to be off, and I'll request you to do the same when you do your analysis. Now, before we move away from here, it's important for us to create a field output that sort of collects all the information that I'm going to need. So it's important to go through the stresses, make sure that you're picking up all the stresses that you're going to need. Make sure that you pick up all the strains that you're potentially going to need. Now in this, it's important for you to select the section strains and curvatures, SE, besides the longitudinal and the shear strain components and the plastic strain. You also want to select the section strains. These are going to be the curvatures, phi, the strains, epsilon, centroidal, the section strains, what we're talking about. Those need to be selected. So you'll select SE. You can go ahead and select SPE as well. That will give you the nonlinear general section. That will give you the plastic curvatures and so on, and all plastic axial displacement. So besides the stresses and strains that you normally pick, you also want to pick up some of those section strains and curvatures. You want to pick up all your displacements and rotations. And then the important one is forces and reactions. Here again, you want to pick RF, which is the reaction forces and moments. But you also want to pick SF, which is the section forces and moments. The section forces and moments are very important because that's where your bending moment diagram is going to be located. The bending moment diagram will be SM1, your axial force diagram will be SF1, and so on. So you need to make sure that you write that, otherwise you won't be able to see it or post-process the file accordingly. Not that you're going to do a lot of that. I'm not asking for too much of that in this exam. If you were using rebar, remember there's a tab down there. You can request for output for rebar. So if you had defined the cross section as including some rebar layers, you would have used that. And output at the shell beam and layered section points, right now I'm leaving it at default, which means that it's going to give us the stress values at the top, at the center, and at the bottom. If you wanted more locations through the cross section where you wanted stresses, you would click that button and type in more keys, like for example 1, 2, 3, 4, 5. Right now it's 1, 3, and 5. You can ask for 2 and 4. If you want more, then you have to increase the number of integration points through the cross section. We don't need to do any of that at this point in time. So leaving it at the default should be just fine. So those are the output parameters that you need to request. After which you get to interaction. There's nothing really for us to do here. We get to the loading and look at the boundary conditions. We've specified fixed end boundary conditions. Now, if I remember this right, you have to do a problem that has an axial force. Is that right? Yeah. If you have to do a problem with an axial force and you completely restrain both ends, you can't really apply an axial force, right? So you have to make sure that at least one of those ends, the end where you're applying the axial force, is free to undergo axial translation. You understand what I'm saying? So not all U1, U2, and U3 will be restrained. In fact, U1 will be free at the node where you're applying the axial force. It has to be, otherwise the force will just go into the foundation. I thought of many other clever ways of giving you the problem. I almost gave you a problem where there was a thermal load, so it would expand and it would get an axial force, and then I decided that maybe I was making your life too difficult, so I gave up on that. I just gave you the axial force of 0.2 py. It's easy enough. You can calculate 0.2 py, apply it. Just make sure that you don't restrain it at that foundation, otherwise it won't apply the axial force. Right? But I don't have an axial force, so I can have U1, U2, and UR3. Both ends are fully restrained in the initial step, and of course that's propagated. Hey, I left U1 equal to 0. How about that? I was thinking about applying an axial force. That's what it means, but I hadn't applied it yet. For the case of axial force equal to 0, it's not going to matter. And then the loading, in this case, I've applied the loading at the same location. Now, there are many different ways by which you can do a plastic limit load analysis. There is a modified Higgs method. You can use an arc length based method. We could have done a displacement based analysis. There are many different ways in which I could have done this analysis that would have given me more answers than what I'm going to get from this. But I decided to just go with load control. The reason I decided to go with load control was because it was simpler and I already knew what the answer was going to be. I know that the capacity is 160 kips. I saw that when I did my hand-to-hand analysis. So I applied a load of 170. I know it's never going to get there. It's going to get to 160 and crash and burn. Right? So what I'll get from this analysis response will be behavior that looks like this. It will go up here and it won't be able to propagate in this direction because it will never find equilibrium for 161 kips. It can't. The plastic load is 160 kips, after which it just becomes a mechanism and starts falling. So if I apply the loading in load control and give it 170 kips, what is the program trying to do? The finite element approach is trying to find equilibrium for 170 kips. It's not possible. So it will exit with an error and come back and tell me, I can't do this. That's all right. It went up to the plastic limit load and then told me that. So I can still post-process the results and I have the answer that I'm looking for. If I wanted to push it further out, if I wanted it to go all the way, then what I would do is instead of applying the load, I would apply a displacement boundary condition, which means that I would select that same node, but instead of applying a load, I would apply a U2. And I could give it any U2 I wanted. I could tell it, all right, take this point that's located right here where the loading is being applied. Take this point and subject it to a U2 of 1 inch or 2 inches or 3 inches or 4 inches. I'm not specifying a load. I'm doing the analysis in displacement control. I'm telling it push it all the way to 2 inches. And then it will do this because it understands that I just want to go to the displacement. I don't care what the load is. It would give me a better response. It would give me that mechanism that occurs and how it undergoes plasticity. Do you know what I'm saying? And there is a third way to go about doing this, which is the modified Higgs method, which is neither load control nor displacement control. It's actually an arc length control, which means that it uses arcs along the load displacement path to continue the analysis. So every time it proceeds, it's neither proceeding with delta P nor with delta delta. It's actually proceeding with an arc on the P delta response. And what it does is it will be able to find the equilibrium at every arc increment. And we've never talked about it, so we're not going to talk about it now. It's the modified Rix method of doing this analysis. It should be covered in your advanced finite element course. 675, if you take it, it should talk about your advanced analysis method that consists of the modified Rix approach. The modified Rix approach is really useful when you have a load displacement curve that does this. When you have a load displacement curve that starts coming down, after you hit the peak, load control will not be able to find the solution. Displacement control may or may not be able to find the solution, but the Rix method will always be able to find because it will be using an arc increment. It's always using a positive increment on the load displacement to find the next state of equilibrium. So from the current state of equilibrium, it throws out a little arc to find out where equilibrium is possible. And if it can find equilibrium anywhere around that circle, it finds that point and proceeds further. And there's a whole nonlinear formulation that Rix developed and been implemented as the modified Rix method. But that's not something that we're going to talk about. Of course, if your load displacement curve is doing this, even the Rix method will have a hard time finding a solution because it will have a very hard time finding a location point that's right there. In that case, you'll have to switch over the analysis method to explicit analysis because that will probably be the only one that can find a solution for you. But in any case, we are doing it in load control, force control. You can do it in displacement control. I'm not going to stop you. But remember, if you do it in displacement control, then the force here will be the reaction force. Because if you specify displacement, you get reactions. If you apply a load, then it will be CF, or the concentrated force at that point. You understand the difference, right? So when I go to plot the load displacement response, if I'm doing it under displacement control, I need to pick up the RF2 at that point. Whereas if I'm doing a load displacement analysis, I need to pick up CF2 at that point. It's obvious, at the same point, you can't specify both the load and the displacement. You can specify one, either the load or the displacement. So if you do the analysis in load control, then at that node, you can pick up CF2, which is the concentrated force it's applying. So you'll plot CF2 versus U2. But if you're doing it under displacement control, you'll have to plot RF2 versus U2, because there'll be a reaction force at that node. It will condense out that displacement. I'm sure you're familiar with static condensation. Because you're specifying a displacement, it will statically condense out that individual degree of freedom, and it will appear in the reaction force when it completes the problem solution, rather than in the applied load. All right, so I applied minus 170 kips. And then we created a mesh. The mesh was really simple. In this case, I'm going to have to use my query tool. I've forgotten what I was using. There we go. The element type that I'm using is B22. It is a second order beam element with two nodes. Let's see what it is. I divided, it was a 100-inch element, you remember that? 100-inch beam. I broke it up into 10 pieces, so I have 10-inch segments. Now, did I have to do 10 inches, or could I have gone with 20, or could I have gone with 75-inch segments? I potentially could have tried a much coarser mesh. In this case, I didn't need to. Maybe about 20 years ago, people spent a lot of time looking at more efficient beam column elements so that you can represent the behavior of the entire column or the entire beam using just one finite element. Because you were working with a 10-story building or 20. Even now, if you're working with a 50-story building, can you imagine how many beams and columns you potentially have? Especially if it's a 3D structure. And you're analyzing, let's say, just the 2D part of it. Even then, a 50-story building with several bays will have lots of beams and columns. And if you represent each beam or column with 10 or 12 elements, by the time you're done, you can have a gigantic finite element model of the structure. And if your solver, what is the solver? The solver is the solution strategy. What is the solution strategy? It's the thing that we've just been talking about, whether it's in load control, whether you're using modified Newton-Raphson, or you're using the Rix method of analysis, or implicit methods, or explicit methods. If your solver is incapable of working with so many degrees of freedom, you're going to run into situations where your finite element model will be running for quite a period of time. Which means that it would behoove you to use a program that has robust solution strategies. Now, what do I mean by robust solution strategies? We never talk about that in class. It would be something that would get covered in your advanced finite element class. Even in your basic finite element class, we don't really talk much about solution strategies. In your basic finite element approach, you've got F is equal to K delta. Is that right? Elastic finite element analysis. So delta becomes equal to K inverse times F. K inverse is easy if you're talking about a 3 by 3 or you're talking about a 10 by 10. But when you start talking about 1,000 by 1,000, K inverse cannot be calculated. Not by the techniques that we're familiar with, not by the techniques that we cover in math classes. Instead, you have to have a solution strategy for being able to solve a series of 1,000 equations together. And there are different ones that are available in different math textbooks. Those are called solution strategies. Even for elastic analysis, if you end up having 10,000 degrees of freedom, it takes a lot in terms of implementing the solution strategy. Let alone you introduce now nonlinearity. Now these equations are coupled. How do you solve them becomes the solution strategy. So there's a reason why I'm using Abacus in this class, or I use Abacus for my work or for my research. It's because I want something that has robust solution strategies. I don't want to be running around trying to figure out what solution strategy am I going to implement. Even if I learned the entire finite element method, even if I learned material plasticity, I wouldn't be able to implement it unless I had understanding of solution strategies. Did we talk about solution strategies? Never. Modified Newton-Raphson will only get me up to the peak. It won't give me anything beyond it. What I need is a modified Rix. Who's going to implement it? Well, who's going to teach it to me first before I implement it? So what I need is a computer program that has robust solution strategies, and that's why we use some of these commercial finite element codes. Of course, you can, for this kind of a simple problem, you don't need a very robust solution strategy. But that's why we're using it. And so when they came up with those finite elements that covered the entire beam or the entire column, the objective was to have an efficient finite element that can still be solved using simpler solution strategies. There was a lot of work done maybe 20 years ago on such a topic. There's no need for any of that anymore because I can always model it using 100 finite elements, and software is capable of taking all those degrees of freedom and has robust solution strategies for me to be able to do any kind of analysis that I want. Does that mean I should have 12 elements per beam column? I don't think so. It really, really does depend on what is it that I'm trying to do. If I'm doing a simple analysis of overall static pushover type analysis, I'm going to have plasticity occurring closer to the joints. I'm going to have plasticity occur where there are largest moments. I don't need a very sophisticated mesh or a very fine mesh to do that. But if I'm doing like a collapse analysis where I'm going to be losing a few columns and then the load will redistribute through the system, it would be better for me to use at least several finite elements along the length of individual beams and columns. That's what we typically do. In this case, I chose 10 elements just because I felt like it. It was not going to make any difference to the answer. And then I selected a finite element. I'm sorry, this is the tool by which I can assign the element type. So I selected that. And when I get to this, remember it is offering me a standard element and an explicit. Now you know what that word explicit is for. If nothing works, everything is falling apart. You probably have an issue with your model. Before you switch over to a bigger solution strategy, you probably have an issue with your boundary conditions or the loading or something else that you've specified. For example, you've taken a truss element and you're trying to model a beam with it. It will never work out, even if you switched over to explicit. Why? Because the physics that you selected does not represent the problem that you're trying to model. You need to understand the physics of the problem, the mechanics that you're trying to capture. If you're using the wrong finite element, there's nothing you can do to get the right answer. Not even changing the solution strategy to explicit. It's important to understand that you can't solve a quadratic equation simultaneously, because that's reserved for linear equations that can be solved simultaneously. If your solution strategy does not agree with what you're trying to do, you will never get the answer, no matter how much technology you throw at it. So at some point, if you find that you're not being able to find an answer and nothing's working out, take a look at how you've modeled your problem. You perhaps haven't captured the right mechanics. Because if you capture the right mechanics and you do it properly, you should be able to get the analysis reasonably faster. Of course, there are still problems like concrete cracking and crushing for which you will probably need to activate explicit because it just won't work out in any other solution strategy. But yeah, before you start going higher order, you might want to look at what you've done, what assumptions you've made in making your model. Anyways, this is the standard finite element. I'm selecting a quadratic element. I've gone a level higher. That means I'm using... Now, most of you know that what is the polynomial that we use to represent the elastic behavior of beams? It's the Hermitian cubic polynomial that we typically use. But that's applicable for the situation where you have t equal to 0. When you introduce an axial force, it really becomes sine and cosine shapes that you need to use in order to solve the same problem. So the elastic behavior follows the cubic displacement function, or you could say that the shape function needs to be a Hermitian polynomial. How do I get that? Well, you remember your differential equation is fourth order, right? You get fourth order W dx4 is equal to 0. So if you start integrating, you get a cubic Hermitian polynomial for your displaced shape. So ideally, you should be using a cubic displacement function. I'm not using it, doesn't even give me the option. The best I've got is a quadratic, right? So I'm going to use the quadratic. But remember, the Hermitian polynomial is needed for elastic analysis first. Secondly, it's used for the case where p equal to 0. So I'm not that worried about the fact that I'm using a quadratic function. I'm using more than one element, am I not, along the length? If I was using just one finite element, I would need to use a Hermitian polynomial. And I was trying to do an elastic analysis. It would give me the most accurate answer. Because the behavior follows the Hermitian polynomial. That's x cubed divided by m cubed. What I mean by that is that the formulation of your finite element, if it is identical to the formulation of the displacement that you get at the end of the analysis, then your answers will be done in one finite element. You will need only one. If your shape function is the same as the displacement function would be in the mechanics space solution. Do you know what I'm saying? If the Hermitian polynomial is telling you it's a cubic and you use a shape function that's cubic, you will need one finite element in order to solve the problem. Because your shape function is exact. Whereas if you used a linear, you're probably going to need a lot more. Or if you used a quadratic, you would need a little more, few more finite elements. In this case, I don't need to worry about it because firstly, it's a nonlinear inelastic problem. I'm going to get all kinds of plasticity occurring, so the Hermitian polynomial is not going to represent. Later on, you're going to apply axial forces that Hermitian polynomial does not work for that. It only works for the case where you have the equation, the fourth derivative of W dx4 is equal to 0. That's your beam differential equation. That differential equation gives you all of 474. So that your matrix method of structural analysis is based on that one differential equation. Of course, if you introduce the axial force effect, you get all of stability or 570. In any case, I selected a quadratic element. I could have gone with a hybrid formulation if I wanted, but I left it simple. It's a 3-node quadratic beam in a plane. It tells you down there what kind of element it is. Now that we've selected the element, we can go ahead and do the analysis. And that's, I had given it the analysis to be done in 100 steps. And watch what it does. It went through all the steps. And at the end, it got up to step 0.96. Didn't quite go up to 1.0. Right? Asked it to apply 170 kips in 100 increments. So it started chugging along. And it couldn't quite get to 1 because the step time was. But if it reached 1, it means it applied 170 kips. It crashed and burned at about 0.96. And what does it tell me? It says, too many increments needed to complete the step. The Abacus standard analysis exited with an error. Please see the message file. And when I look at the message file, which is not uploaded here, it'll tell me I couldn't find equilibrium. I tried, I couldn't find equilibrium, so I went ahead and stopped. It's because I did the analysis in load control. If I had done it in displacement control, it would have pushed it to the displacement and given me a converged load associated with it. And that's the result that I got from doing this analysis. I can plot the displaced shape. I'm sure you recognize what it looks like. It looks like it the way it should. I can look at the plastic moment. And in order to be able to, I'm going to convert it into a then be able to read it, I'm going to plot it on top of the undeformed shape. I'm sure you're agreeing with what we're looking at on screen here, but I'll explain it in a moment. Let me specify the limit to be 1500. Now, since it has gone through and done a fully nonlinear analysis, it's gone a little bit above 1500 as well. But there we go. That's the same bending moment diagram that we got from the event-to-event analysis. That's 1500. This is minus 1500. That's plus 1500. And if I wanted, I could look at how this is happening. I could probably run a video, and it's going to show me how the bending moment diagram. Watch how the bending moment diagrams are working. You'll see one of them hit 1500. Will probably be the same one that occurred first. There, that's hinge number 1. Then that's hinge number 2. That's hinge number 2, and then the final hinge occurs at the end. Of course, I can look at the load displacement curve as well. In order to look at the load displacement curve, I'll have to select that node, save CF2 and the corresponding U2, and then plot them with respect to each other. If I did it in displacement control, I'd plot CF2 and RF2. So I'll be able to get out all the outputs that I need from this analysis. It's fairly simple. I didn't change the geometry of the beam, right? When we did in the exam, they're all just the same length. Only the cross-section changes. So you should be able to do it reasonably fast. But there is I will remind you to read part 3 a little more carefully. Part 1 and part 2 will be straightforward. Part 3 will save a day for it or two. Just to look at what's going on there. Okay, are you okay with this? We've talked about it enough. Do you want me to plot the load versus displacement? It's just the same. You select that particular node, pull out CF2 and U2, and then plot them with respect to each other. And the response will look very similar to what we just have looked at. There it is. It's telling me that CF2 reached a value of about minus 163.9. Of course, you can select that node and plot the CF2, and you find the load displacement curve to be very similar, not identical, but very similar to the load displacement curve shown here. The differences will be due to the fact that we are using method 1. It's integrating the entire cross-section response in order to calculate. This is method 2, where you've idealized the moment curvature behavior to be elastic plastic. So there'll be some minor differences associated with the occurrence of plasticity and so on. Okay, so that takes care of